I am Kaushik Kolodia. I am going to present about the determine of average reservoir pressure in a well test analysis, which was given as an assignment by our faculty Dr. Pavan Gupta. So let's start the presentation. I hope you enjoy the video. Topic is determine of average reservoir pressure contain. We have to understand about the what are average reservoir pressure used for and determining drainage volumes of well, and also most important things, the determining average pressure in bounded reservoir. First things is what are the average reservoir pressure used for. Use the average reservoir pressure used for characterizing a reservoir, and second things is computing its oil in place and predicting the future behavior. In characterizing a reservoir, pressure are used to relate the amount of production in a given interval of time to the pressure drop. If the pressure drop is small per unit of production, a clue is given to the existence of a water dry or drainage or large reservoir volume. If there is a pressure drop is large for the given amount of production, this may indicate drainage from a small sand lens or fault block. In addition to this semi-quantitative use, pressure find a quantitative use in volumetric balance calculation of oil in place in a reservoir. For this purpose, average reservoir pressure are required. And second things is determining the drainage volumes of wells. First question arises, how does one find the size of this drainage volume? We first note that at a semi-steady state and make assumption that each well in a reservoir drains a volume proportional to its production rate. Prior to this time, each well in a reservoir tends to drain an equal share of reservoir. Simple example to illustrate this concept is shown in a figure for a 1.1 gm2 rectangular reservoir where one well produces at twice the rate of the other. In this figure, as you can see, movement of the drainage boundary. Movement of the drainage boundary change with time to time. This example was obtained by using EI function to represent the pressure drop at a wells and imaging to reproduce the boundary of this two well reservoir. By summing the effect of EI function, then delta P was calculated. So, in presentation, by using each value of time, equipressure contours and flow lines are drawn. Some of the flow lines are shown in figure 1a and figure 1b in this presentation. Note that each well initially drains one half the reservoir and that the boundary gradually shifts until each well a volume proportional to the rate. The time required in this case to reach semi-steady state where each well drains a volume proportional to its rate is K into T upon 5 mu CTA is equal to 0.7. In other words, for a assumption for well 1 is equal to 2, for well 2 is equal to KT upon 5 mu CTA is equal to 1. It means then time required to reach a semi-steady state. Okay. Then we have to move in fourth point. In a real reservoir with non-symmetrical drainage area shape, the transit period may be very long compared to symmetrical reservoir. It means that transient period is more in a non-symmetrical drainage area shape compared to symmetrical reservoir. In addition, the discussion presented so far is for homogeneous reservoir, but in heterogeneous reservoir, time required to achieve semi-steady state in such a reservoir may be 10 to 15 times as long as in homogeneous one. Studied by Lefkowitz and other. Figure 1 illustrates the two limits on drainage volume. One limit volume is obtained by allocating volumes in proportion rate, and second thing is very important, other is obtained by dividing the reservoir volume equally among the all wells. Okay? Even at time prior to steady state, we normally use the first limit and assume that drainage volume are proportional to production rate. Third point is determining average pressure in bounded reservoir. Here we will examine two useful methods. First, Matthews-Bros-Hedgebrook, and second is modified Muscat method. Here we understand about MBH P star method means Matthews-Bros-Hedgebrook method. Steps of MBH P star method. First, you have to draw Horner plots delta P versus time and estimate the ETR, MTR and LTR. Means early time region, middle time region and late time region by using given data. Then you extrapolate the middle timeline to Tp upon delta T is equal to 1 and extrapolate and other. The second is estimate the drainage area shape, and then you choose the proper curve and estimate the P star. Let's take a disadvantage and advantage of this method. First advantage is the estimating the static drainage area pressure, or that it doesn't require data beyond the MTR. Estimating static drainage area pressure means average reservoir pressure. It is applicable to the wide variety of drainage area shape. Disadvantage is requires knowledge of drainage area size and shape and estimate the fluid and reservoir property, which are not always accurate. This is the disadvantage. Let's take one example. Find the average reservoir pressure so you easily understand. First, problems is given by in John Lee book. First is the well was produced for effective time of 13603 hour at a final rate, means TP is equal to 13,630 hours. Other data including the in presentation U0 mu05 B CT RWRE, and we have to find the K value by using slope M by plotting the Horner plots. We need the first to find the P star. Here you can, as you can see in slide, the Horner plots they have plotted, and this is the very important graph for estimating the average reservoir pressure according to your drainage area shape. We need P star, the value of PWS on the middle timeline at a TP plus delta T upon delta T is equal to 1. Then you can extrapolate the middle line to TP plus delta T upon delta T 1 is equal to 1 and extrapolate pressure P star. Here, as you can see, we note that pressure increased by 17 psi each cycle. So we can add it 2 times cycles to the value of P at a TP plus delta T upon delta T is equal to 100. So P star is get 400. 4577 psi. We assume that the well is centered in a square drainage area. So figure 2 applies. To use this figure, we first calculate the 0.000264 kT upon 5 mu Ca is equal to, we find 7.45. We have to move in the shape graph and take in x-axis take our result 7.45 and get in y-axis p star minus p bar upon 17.6 q mu b upon k is equal to find 5.45, as you can see in the slide. Therefore, this is the calculation for easy calculation, and we can find p star is equal to 4411 psi. Thank you.